3.3. Okay, and then they sent up satellites to measure this radiation, and what they found is that basically the temperature in all the directions is the same. Well, and they made maps of the temperature. This is this is the night sky, if you like. I mean, 4 pi squared. And you see that there are some areas where it's a bit hotter and some area where it's a bit colder. But this is 1 part in 1,000. So how does this come about? Well, the solar system is not at rest with respect to this radiation, but it's moving towards this direction, and therefore there's, again, this Doppler shift. Doppler shift, everybody knows what Doppler shift is? This is the effect that when an ambulance comes towards you, you hear a higher tone than when it's moving away. So when you're moving towards the radiation, it looks slightly hotter, and it's this direction. So if you subtract this movement, you get this picture. Hello, this picture. And you amplify, of course, you always amplify the fluctuations. And then you still see here, this is the Milky Way in the foreground, and you can remove the foreground to end up with this picture. This picture got another Nobel Prize, because what you see here are the tiny temperature fluctuations, 1 part in a million, in the afterglow of the Big Bang. And there are some areas which are slightly denser and therefore slightly hotter. And these are the points where gravity attracted and then galaxies form. So these are the earliest pictures of galaxies. This satellite was Kobe. They sent up another satellite called WMAP, which did a more precise measurement here. Looks like this. So these, again, are the same fluctuations, just with better resolution. In the past months, they launched another satellite called Planck, which is going to improve even more on this picture. So this is a nice picture, but this is not the data here. I mean, we are not looking at a particular spot and then trying to pinpoint the galaxy on the Hubble Space Telescope picture that corresponds to this dot. But what you do with this thing is you basically Fourier transform it, and this is the important graph that everybody draws when looking at WMAP pictures. So what is plotted here is the amplitude or the power of the fluctuations plotted against kind of log of the scale of. I mean, these are the largest fluctuations angle-wise, and these are the smaller ones. So you see there's a peak here around 200, which is roughly the opening angle of 1 degree. And you see this in this picture as well, because you see grains here. And these grains, I mean, the typical grain size here is about 1 degree. So what you see here, the black dots are the data from the picture on the previous slide. And what you can do is you can come up with a model of how the universe expanded. How much matter there is, how much density, how fast the expansion is, how the cooling works. And then you can fit your model to these data points, and this red line is the fit to the data, and it fits except for the early parts and the later ones. It fits extremely well, and it pinpoints our understanding of the universe. From this model that produces this red line, you can understand exactly what is the average density of the universe, what is the average density of normal matter in the universe. How fast is it expanding? How big were the early fluctuations? So this is the real output. There are 7 parameters in this model, and with this graph you determine these 7 parameters. Okay, so that's state of the art in cosmology, and now that we have all these data points here, cosmology has really turned into an observational science rather than a speculative one. Okay, so this is a sketch of what happened in the universe. So here is the Big Bang, and time is going in this direction. We are here. Right? That's us. And here, this goes, I mean, this is not to scale, but this goes back in time. And because stuff cooled when it propagated forward in time, when we go back in time, stuff gets hotter. And you see that here is us, and there's a star, and there are a couple of, I mean, this is supposed to be a photon, so there's light, and there are some neutrons. But when you go back in time, I mean, here the first galaxies form, but then when you go back further in time, at this boundary here, the universe is so hot that the electrons boil off the atoms. So what you see here, beyond this line, is you see the nuclei of the atoms and the electrons separately. It's a plasma. You have freely floating charged particles. And this is where this borderline is where this cosmic microwave background that I've been talking about for the last 10 minutes is coming from. Because when you have freely moving charged particles in a plasma, you cannot transmit electromagnetic radiation because it's scattered from here. So, and at some point, all the electrons found their nuclei, and then only neutral stuff is around. And then from this point on, photons, light particles, can propagate. And therefore, we see this line of last collision, which was roughly 150,000 years after the Big Bang. So a very short time, just 150,000 years. But we cannot see with optical instruments beyond this line because light is not going through. It's opaque here. So we have to use other methods, and here the same thing happens with the nuclei. That it's getting so hot that the nuclei don't stick together, and the individual protons and neutrons fly around in this era, and then even the protons come apart and the elementary particles float around in something that's called quark-gluon plasma. But as I said, we cannot look into this time with optical means. We have to find other ways to get data from such physics, and this is my next subject, which is particle physics. And we try to recreate conditions like here in a particle accelerator. And eventually I will talk about this area, which is where string theory lives. Okay, so let's move on to particle physics. Okay, so as you can imagine, so far we looked at the biggest things you can imagine, the whole universe. Now we want to look at tiny stuff, the inner workings of atoms and other things. So I want to look at small things, and if you want to look at small things, what do? You use a microscope. But you probably all had the same experience in school. I mean, here you can tune the magnification of the microscope, and you learn that it doesn't make much sense to use a magnification that is stronger than 1,000 times. I mean, one of these things is typically 1,000 times, and it doesn't make sense. Why doesn't it make sense? Because you're getting in the vicinity of the wavelength of the light. And you can't observe stuff that is shorter than the wavelength of the light that you're observing with. So a microscope won't work for particle physics. So you want to investigate smaller things, you use something else, you have to replace the light. For example, you can replace it with electrons. This is an electron microscope. Because the electrons, as waves, have much shorter wavelength. And in fact, the higher energetic, the faster the electrons are, the higher the energy, the shortest wavelength. So I can use a bigger microscope, or eventually stuff is too small for the wavelength of this electron microscope. So what do? You increase the energy, you build a bigger microscope, and here it is. That's the LHC. But actually the LHC is just a big electron microscope. Well, actually a proton microscope. They're accelerating protons. But the idea and how it works is exactly like a microscope. It's just bigger because you want to produce higher energetic and therefore shorter wavelength stuff to probe what you want to probe. In this example, you want to probe the inner workings of a proton. So this is the line, it's underground, right? There's a 26-kilometer circumference ring near Geneva. Here you see Geneva Airport, here you see Geneva, Lake Geneva, here are the Alps, right? So that's the scale of things. Most part of it is actually in France, not in Switzerland. But this part here is, the French-Swiss border is somewhere here. Okay, so just a quick reminder of what is the stuff we're looking at. So this is supposed to be an atom. I hope you've seen this before. So an atom consists of a nucleus and the electrons that orbit around the nucleus. So electron here in this picture is the blue thing, and from all we know, the electron is, in fact, a point-like elementary particle.